closer to the. This is Honglin Wen.
Yeah.
Who's going to be talking to us about physical consistency and uncertainty quantification in scientific machine learning. Leave questions to the end unless you prompt the audience for questions.
Yep.
We'll definitely have time for them. I'll hand it over to you.
Okay.
All right. Thank you.
Okay. Thanks, Miranda. So originally I come from China, but I'm not from China today. So yeah, I just came to Leeds this morning from London. Currently, I'm a research fellow at Imperial College. So it's very happy to be here to give a talk. Indeed, it's my second time this year to come to University of Leeds. During summer, I attended the Euro conference, which is held in Leeds this summer. So that was my first time to come to Leeds. Yes, I got this invite from Miranda just by, accidentally, I think. Yeah, because I was in the mailing list, so I got some intervention with Miranda. So, and I think the idea to form the scientific machine learning committee is cool. So if you Google scientific machine learning committee, I think you can only find this community in Leeds. Seriously. So I was very curious. So when Miranda asked me if I'm going to present in person or online, so I decided to come here to get more involved with you. So today I'm going to talk about some specific aspects about scientific machine learning. Okay. So a couple of words about ourselves. So we have the Analytics and Market Lab at the Imperial College London at the Dyson building, Dyson School of Design Engineering. So the design engineering, I think this major is also not very common in both UK and all over the world. So the design is not that, it's not about art or something. So we mainly do some work about data science and data-driven design. The design is most often relevant to the inverse problems, which is somehow relevant to some of your research. So the PI is Professor Pierre Pinson. Okay, we know, the AI, since you could say the AlphaGo or the ImageNet, the AI has caught great attention all over the world. And in the science domain, maybe, we know the AlphaFold is maybe a signal or something about AI for science. Yeah, this paper was published in 2021, maybe. Yeah, the work was done in 2020, and it won the Nobel Prize last year, right? So they use AI to predict the structure of protein, which was regarded as a very, very difficult scientific task before. So for a group of scientists, even you have very advanced instruments or something, you may spend like half a year to identify the structure of the protein. But after accumulating a lot of data, and they train a very smart AI model which can predict the structure of protein within seconds, right? It's a very good achievement. Another thing, we know that, maybe some of you might know that the AI has revolutionized the climate science, the weather science. So my mentor PI, he once worked at the ECMWF like 10 years ago or more than 10 years ago. Yeah, Pierre was a statistician. So when he went to ECMWF, he said maybe we can train some machine learning models to predict the weather. At ECMWF, it's a place full of physicians. So they believe the ODE model, the PDM model, the physical models. They think it's impossible to train a machine learning model that can forecast the weather. Yeah, at that time, 10 years ago. But for a very, very long time, we think it's a very complicated task. Even by designing the physical model, you have to run the PDE at the supercomputer with a very, very heavy computation, right? And so only, I mean, most of the models are developed by the developed countries, like the ECMWF in UK has the best models in the world. But like 2 years ago, yeah, indeed this work, yeah, I talked to the authors this summer. Indeed, you cannot imagine when they decided to do this work 3 years ago. This work was done by some engineers at Huawei, a Chinese company, 3 years ago. When they decided to do this, they did not have a very, I mean, very ambitious goal. Just their customer run to them to say, oh, we face some big challenge to predict the renewable output. Can you help us? So they decided to do that. And then they never imagined they can revolutionize the weather and climate science. But this AI model was very successful, and it raised the attention all over the world to look at AI for weather prediction. Like if you talk to the scientists like at ECMWF, they are embracing AI, right? They have the AIFS, and now I think they are updating their model. Yeah, so we know now AI, I think if you talk to any scientist from any area, we would say, yeah, AI is a very strong power to speed up our scientific discovery, right? Maybe for scientific discovery or simulation, etc. Indeed, the deep learning techniques, or these techniques has, I mean, all of these techniques have been very mature. It has evolved for more than 10 years, 20 years or something. If you look back to what Geoffrey Hinton has done, that was like 30 or 40 years ago. So most of techniques have been established for the recent decades, which driven the now very advanced models. So let's say now the neural network based model has run, due to its flexibility, has gained great attention, right? So what you need is just training data and a loss function, a very good loss function, and very optimizer. So most of the advanced are just about, yeah, I mean, also the model types, the transformer, whatever, attention mechanism, and a lot of optimizers like Adam or anything. So the thing is that we use, so in short, if we have a bunch of data, we can train the neural network models like transformer, whatever. But if you design a loss function and using the optimizer to estimate parameters, that's it. But when we say the scientific machine learning, what do we say when we say scientific machine learning? What do we mean? In my view, yeah, and now if you talk to several people in this area, people say, yeah, the machine learning models are good, but there are some drawbacks. Yeah, first, you need a bunch of data, right? And it does not contain any constraints. So we know. So sometimes we call it as domain knowledge or something, or you could say it's a physical prior. If you analyze this problem in the Bayesian view, you could say, yeah, if we use the prior in it, we can constrain the hypothesis class. Then it's easier to train the model. That's right. So the idea to combine the scientific principles, I mean the physical principles and the machine learning methods. So that is what we call scientific machine learning. So I want to stress that scientific machine learning is not just apply machine learning to scientific problems. We need to design the new model or methods for our own scientific problems. Generally, we could say for most of the scientific problems, we have some the PDE models, right? So we have some governing equations like the Navier-Stokes equations, or even you have only some algebraic equations. So you have equations that can maybe evolve over time or the space. So that constrain the data you will observe. So in the past, I think most often, yeah, after the 2018. So there are two mainstreams in this field. I mean, which get very strong success. So the first is about what they call the physics-informed machine learning neural networks. Most often, so it's based on neural networks. So the second is the neural operators. So for the physics-informed neural network, the idea is that we can train the model just using the governing equations. We don't need to train the data. So for the neural operators, that means we given a class of PDEs, we can train the map, I mean the solution map, from the parameters to the solutions. So that is the mainstream models here. But if we analyze this in the view of parameters estimation, I mean in the optimization, so it's not magic in it. So the physics informs loss, so it's just a loss with respect to the governing equations, right? So I mean, if let's say we predict the solutions, using that solution, we can calculate the loss, the physical loss defined by the governing equations, boundaries, let's say. And so if we have a data set, we have empirical data loss. So I mean, we compare the predictions with the ground truth, right? So that is empirical data loss. So if we combine these two terms, it's very interesting to say, oh, it's just a constraint optimization problem. That's it. So previously, people sometimes combine these two terms naively, but if you think it in a more principled way, it's just a constraint optimization. But I want to say, yeah, as we take into the physical constraints, so it can enhance great data efficiency, right? So after we take into the constraints, we narrow the space of the parameters. So we need less data to train the model. So that is what they want. But at the same time, because we care about the solution of the PDE, so these equations require the solutions to satisfy the equations, which means the consistency of the equations. So that is required by its nature. It's not required by us, right? But although we have done a lot on this, but there are still some challenges. So let's say these two pictures are drawing from a manuscript by ECMWF. If you say, so the precipitation forecast by the AI model, you could say, I mean the gray parts are negative values, but obviously the precipitation cannot be negative, right? So we know for the MSE terms or something, the AI models are very good. It can even beat the physical model within 3 days or something. It can beat the physical model, but the right panel is issued by the physical model. Obviously, there are not such kind of silly issues. So this is a kind of what I say the physical consistency issue. The second is, yeah, if you just look at the PDE in the lab, yeah, it's deterministic. Yeah, given a toy PDE, we know it's deterministic. But if we analyze the problems in practice, there are a lot of uncertainty. So let's say for the weather, we know, so if you use the weather information for some uses, you will know, indeed, for the weather agency, they will always issue the probabilistic forecast. They will not give you just 1 point forecast, because the world is random, and it maybe the initial condition, maybe the boundary, maybe the hyperparameters, or the force terms, or something, or anything. So, and I mean the requirements is by several applications we need. Let's say for the safety critical decisions, it requires to know. It requires us to communicate the uncertainty of our forecast, our predictions, instead of just a point. Let's say if you are the users, I just communicate a point. You will be curious about how confident it is about the point, right? And for the noise data, we know, yeah, we cannot learn the function perfectly. And for the downstream optimization or control, it requires the uncertainty. And indeed, for several important applications like the weather I mentioned, what they have, I mean, for even the physical models, they always issue the ensemble forecast. And by the way, so I don't have too many slides. If you have questions, you can interrupt me during my presentation. So but now the AI models are trained to as a deterministic model. You can, yeah, I mean, for most of the models now, it cannot communicate uncertainty. So in my view, these two problems are what we need to solve in the future. So let's talk. Let's dive into them one by one. So for some problems, I mean, if we want to ensure the physical consistency, for some type of problems, it's relatively easy. Let's say for this precipitation problem I mentioned before, it's very easy. You can just enforce the value to be non-negative, right? Just have a layer, or if you have some two-sided bounds, you can just bound the output. It's very easy. Or for some applications, it becomes more tricky. Let's say you have some equations to be enforced. Yeah, let's say like for the climate downscaling. So it requires you to, after downscaling, you need the sum to be the original value, right? So that's the equation. You need to embed this equation into the model, rather than just have a bound to the outputs. But it's still relatively easy to deal with. You can, let's say, I mean, for equation, you can predict parts of the values, and you using that equation to, I mean, to calculate the remaining ones, right? So this idea has been used in several works, like in the climate science, or even in the optimization, learning to optimize this kind of ideas. But let's say if we just think it more broadly, let's say we have some equations and some constraints, some inequalities to enforce. How should we do? So indeed, let's say if we just have an AI model, so I mean, using the model off the shelf, so the outputs might violate the constraints, right? So, but after we get the predictions, we can easily adjust them to the space, to the feasible space, right? So let's say we can here the left panel is a convex set. It's very easy to project to the set. So you can also define a optimization problem to minimize the 2 points. I mean, that is indeed the projection process in the convex problems. But the thing is that if we want to have an AI model that can satisfy the constraints by nature, how should we do? So the idea the idea we have, yeah, we use this in our work. We can have the projection as a layer. So it's about maybe in physics this is termed as a differentiable simulation or something, or it's a differentiable optimization. You can have a layer into your neural network after the normal layers of the neural network that will predict some intermediate values and then pass into the projection layer that will map your intermediate predictions back to the physical space. So let's say for sets like for some simple sets, the boxes, normal balls, or polyhedra, these kind of sets, it's quite easy. You can have the analytical projection layers. But for general convex sets, it's still doable. So the projection layer can be defined as a differentiable convex problems. So you embed the differentiable convex problems into your model. So that will fix the issue. But what about more general? So even non-convex problem, how should we do? To be honest, very few people have been thinking about this problem. But I have an idea. So still, you can still use it. Yeah, let's say you can use some unruled optimization as a layer. So as I mentioned before, anyway, if you just want to satisfy the constraints, you can always define an optimization problem. To minimize the distance between a point in that feasible space and the intermediate prediction. You just need to minimize the distance. Then the solution will give you the closest point in the feasible space, right? So, but the thing is that you can do that for the very, very general problem, but we cannot give you guarantee. So even, if it's non-convex event, so although we can satisfy the constraints, but to be honest, I think it's still fair. Anyway, if you do not have this kind of layers, your predictions violate the constraints anyway. So although we cannot promise that's the best, that it's feasible. Okay. So that's about the physical consistency. About the uncertain quantification. So we know there are. So as I mentioned, in the lab, if you manipulate a PDE, there is no randomness, right? but indeed, let's say if we, for example, if for the Earth system, for the climate modeling, obviously you cannot have the accurate model even. So anything involved, like the parameters, the boundaries, the initial conditions, there might be some randomness, right? And maybe some even missing physics or some the numerical uncertainty that we know we solve the problem use the numerical methods, right? So we know it's a numerical solution. It depends on its own error tolerance or your algorithm or something. So so in practice, the uncertainty cannot be avoided. Let's say for a very good example, still in the weather, when we predict the forecast, when we forecast the weather, let's say for next day or something, what do we have for the initial condition? So we do that by the data assimilation. We use a lot of data from the observation on the ground and also from the satellites. We fuse all this information to guess the state of the Earth. So your guess is likely not true. So for most of the time, it's not true. So so the best we can do is to say, maybe we can have a distribution of the initial condition and then propagate with the time. Okay, so that's what we do in the numerical weather prediction. So I mean, for almost every problems in practice, you cannot avoid the uncertainty. For the uncertainty, so let's say, but even for the most simple problems, let's say only we have uncertainty in the initial condition, we want to propagate uncertainty to our solution. It's still very, very hard. Although theoretically we can do that, so it's just a transport of the probability mass. You can do that, but even for this very simple case, it's computationally intractable. So if we want to do that, so what we can do is by the Monte Carlo sampling, we can get sample from the, I mean, so the orange space, the initial, let's say the initial condition, we get samples from it, and then using the scenarios to propagate over the time or something, right? You will get the scenarios in the solution space. So yeah, it reduces the problem to several independent run of your PDE model or something. So that is, I mean, that is in the first principle, in the physical model, that is how we deal with the uncertainty. So let's say for the numerical weather prediction, what they do is to draw the probabilistic scenario from the initial space for the, I mean, the initial condition to get the distribution. And let's say for the ECMWF, they get like 50 scenarios from the initial condition and then run the PDE. But it's still very heavy, you know. On the other hand, I think I need to say, uncertainty is not something terrible. I mean, sometimes it's very helpful. So let's say for the weather forecast. So I quote these conclusions from the ECMWF. They claim that by using the ensemble forecast, there are huge economical value by you leveraging this kind of uncertainty information. And if you are doing something with the design, I think you need the uncertainty. Let's say for the ChatGPT model, indeed is a generative model. So each time when you prompt into it, the answer is different. Let's say you want to design some chemicals. Yeah, you will never want to get a single plausible design. So if we can quantify the uncertainty, it can be leveraged as a set. I mean, when we want to design the model, some statistic of measures are very critical. So the first is the calibration, which means the capability between the predictions and the realizations. So let's say if we have intervals, we need the need the intervals to be consistent with the real realizations. So, and we also want the distribution to be sharp, which means to concentrate around the real observation. But in the very, strict rules, we can also use what they call the proper scoring rules in statistics. You can use this as a measure, but maybe you are more familiar with the log score. So if you train a generative model or something, always you use the log score. I mean, if you use the maximum likelihood, you can just use the log. That is also a proper score, but it's a local score. So for the uncertainty analysis, a very natural way is to think about this problem in a Bayesian view. We think the weights of the neural network follow some distribution. Then, so by draw different values from that distribution, then the model will be different, right? So by drawing different weights from, I mean, if you calculate that distribution, after each time during the inference, each time when we draw the scenarios from the distribution, we can get a unique model, and we can inference with that model. This will give us the uncertainty characterization of that, right? But still it's computationally is intractable. So most often we need to use some approximate methods like MCMC or variational inference, or deep ensembles. The deep ensembles is just a mirror of what I mentioned before in the physical models, where that means you train a group of neural network model. Yeah, it sounds very intuitive to do so. So yeah, we have also utilized this method before. Also in the PIN area, they use this idea. They use the Bayesian neural network to predict the solution map and propagate the solution the solution map, this function with the equations to get the other terms. But I have to say, most often this kind of Bayesian neural network models, they cannot give you a very, so they have the very limited flexibility, and the ensemble spread is very limited, which means they are very sharp, but the distribution is not consistent with the real observation. It's also reported in the recent paper by ECMWF. They analyze a lot. Yeah, still now a lot of people want to do the AI models, the probabilistic AI models for weather forecasts. They try to use these kind of ideas to do some deep ensembles or something, but they cannot characterize the distribution very well. But we can still, if we think about I mentioned the probability mass transport before. So if we think about this problem in that way, it's very natural to link this problem with the generative model. Yeah, as I said before. So what we need to do is just to find a transport from the initial distribution to the solution distribution, right? So that is exactly what the generative models do. So you have a prior distribution, then you learn a map, maybe a flow or something, then to the final solution or observation distribution. So what we have to do is to do the distribution matching. I mean, let's say the PY is the predicted distribution of the neural network. Then you have your observation. Maybe it's not we have just one sample, one observation, not instead of the pure distribution, right? But what we need to do is to do the distribution matching, to match the predicted distribution and the distribution in the observation space, right? So during the past years, there are a lot of models, the VAE, normalizing flow, the GAN, diffusion, or anything. But to do the distribution matching is still very, very, very tricky. So let's say for the GAN model, so it needs the adversary training for the VAE. What you use is just a upper bound. For the normalizing flow, still it cannot be very scalable. So what we this idea, I mean, in the physics informed area, yeah, they still use this idea. Let's say, I think although the diffusion model is very popular now, but to be honest, I think the GAN model is very, 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 very flexible. So several people use it for the scientific machine learning area. But as I mentioned just now, the one thing that's tricky is about the adversary objective. So you need to train the generator and the discriminator. So in the adversary way, so most often it's very unstable. What we can do? So yeah, we have another idea. Yeah, I mentioned, we can use the proper scoring rule, right? Remember that? Indeed, we can train the model. We can train the generative model with the proper scoring rule. That will give you the very direct and very strict distribution matching. Then we still keep the flexibility of the GAN model, and we can solve the training issue of the GAN. Now I have talked about I think most of the relevant advances and what we have done, but still for the scientific machine learning, if we want to characterize the uncertainty quantification, it's still very tricky. So let's say if we think about the physics constraint model, so most often we do not have an explicit likelihood. That is a very tricky thing. So unlike the typical models, let's say we only care about some let's say image or other stuff. So you do not have any equations to enforce it. So often we just use the Gaussian model or something. Then we have the explicit likelihood. But here, yeah, maybe it's very heavy-tailed and multi-model. So we need a very flexible model to do that. But still, we need to trade off the computation efforts. Let's say, although for I mentioned for the multivariate problems, we have the energy score, which is a proper score, but you cannot calculate in a very high dimensional space. It's very hard. So still till now, we do not have a very good tools to do that. I mean, if you want to do a very direct distribution matching, still it's very tricky to do that in the high dimensional space. The second is that in the probabilistic space, we need to ensure the physical laws at every scenario, right? So I mean the uncertainty view is not magic. So it's just like when we calculate the solution map, we must ensure the physical law at each scenario. Let's say for instance in the weather forecast, you need to keep the physical laws at every ensemble forecast, every scenario, right? But and for the explicit equations, it's relatively easy to do that. You can just propagate the prediction with the equations. But sometimes we have some implicit constraints, implicit variables. Maybe you need to solve optimization or something. So that will make this problem extremely tricky to do that. So to sum up, yeah, so the physical priors. So on one hand, we confine the hypothesis space. So it makes the training to develop a neural network model easier. But at the same time, it requires to satisfy the physical constraints by nature. We must do that. And uncertainty is inherent in the PD modeling, right? So, but it's not just a challenge to overcome, but it's also an asset. So we still have a long way to go. Like we need some better ways to calculate I mean maybe the generative models or something in the high dimensional space, and how to ensure the physical consistency at each scenario. And also I want to mention that about the physical laws, I mean the consistency, is still a trade-off. Let's say, why do we need the AI models instead of the PD solving? Because it's fast. But if we want to enforce more consistency, we need to introduce maybe more physical solving or something. It will somehow harm your AI model in the terms of speed, right? Whether we can fix the consistent issue. So it's still a trade-off to do this kind of stuff. So I mean, we still need to identify how to do it better. Yeah. So that's it. Thank you.
Thank you to our speaker. And I will now open the floor to questions. I put in the chat that they should type in their questions if there's online ones. So I'll be checking if there's online questions. Otherwise, does the room have any burning questions for our speaker? Martha?
I was really interested in this idea of including constraints as a projection layer in the neural network. I was wondering if you came across any difficulties with training when you do that, if it makes the model harder to train, or if there's any.
Yeah, it's a good question. So, maybe in the general case, maybe it will there will be some feasibility issues or something. But in general, so if let's say if we reduce this problem as we just want to project the intermediate predictions into the feasible space, this problem is quite easy. So indeed, what you have is I mean, the intermediate predictions are not that silly, right? They are not very far from the feasible space, where otherwise the model is too bad. So somehow the distance is very close. So indeed, you just solve a very simple problems, and for some, yeah, I mentioned before, for some special and simple constraints, you can have the analytical projection layer, so it will not introduce any training difficulties, etc. Yeah.
I have a question also about the projection layer. What projection are you using, and what restrictions are there on the types of equations that you can project? Like if you're just doing the Burger's equation, it's just you just want u out the end.
Yeah.
What restrictions are there on the type of equation that you can project?
Oh, let's say so. So indeed, what we have is the constraints, right, or equations. So when we use the AI model to predict the maybe solution map or something, so it's discretized, right? So what we want to ensure the constraints and equations at that point, right? So what we have is some just linear or nonlinear constraints or equations, right? So when we do that, your linear or nonlinear equations or constraints define a feasible space, right? So when we do the projection, I mean in the general sense, we just try to find a point from that feasible space, and we want the closest point to the intermediate prediction. But at some very special cases, this problem is very simple. Let's say if we only have let's say we want to ensure the consistency at the initial condition. So that's just a very simple equation, right? So what we can do is even use an analytical equation to map your intermediate prediction back to that, where if you have let's say a box constraints, maybe let's say when we solve equations, we know the values are bounded in a box or something, or other kind of very easy constraints, we can get the analytical projection. Yeah. Yes.
Also, on the mapping, I was wondering whether, say, if you don't have a system where your physics is constrained, but there's some uncertainty in the physics equation.
Yes.
Can you use that mapping to get some estimate on the uncertainty in some way?
I'm not sure if I correctly understand your question, but the thing is that maybe let's say maybe your question is about we have some data, so we are not sure about the underlying physics or something, the equations. Yeah, yes, we can do that. The thing is that indeed, as long as we have the data sets, we can always train a generative model to learn the map from the prior distribution to target distribution. But the thing is that like I want to still to mention the idea physical constraints or physical prior. It's just it's a knowledge indeed. It's a knowledge. So if we have the physical constraints or physical model, that will help us to train the model. I mean, maybe by reduce the data volume or anything. So in general, yes, you can do that, but we will not know what do we learn, what do you get finally. We cannot know that, but yes, we can do that. And the learned distribution can, if you estimate the parameters very well, it can match the observation very well. So somehow, so people still use, I think people still use this idea to identify the missing physics, the unknown physics or something, or yeah, like you mentioned, you are doing something with the inverse problems. Yeah, so you could still do that. Let's say you have some let's say you have some missing terms in your model, but you can train a model and then simulate and to guess the terms in your physical model or something. Yeah, that's feasible.
Sorry, just there's a question online, then we'll thank you. So there's two questions. They say, good talk, excellent overview. And then they ask about the projection layer. So they say, two parts of the question. How do you design the projection layer? They say they understand it to be a projection from the model's internal latent space to the physical variables, but how do you know what relationship that should be?
Yes, so a very good question. So indeed, let's say I just say the general cases. Okay, for the general cases, what we have is the physical constraints. Yeah, I mean when we talk about the projection, I mean we know the physical model, and then we have the constraints. So what we use is to use the physical constraints to define the feasible space, right? Then that can define a object optimization problem. Then what we need is just to find the closest point from the feasible space. So the feasible space is defined by the physical constraints and equations, what we have at hand. Yeah, that's it.
And then they ask a bit of clarity on the GANs. So is the idea about using the GANs with PDEs to use the PDEs somehow as a discriminator?
No, not indeed. So so when we use GAN, I mean, let's say for the scientific machine learning view, I mean, what sometimes they call it a random PDE. So it's not a SDE, it's a random PDE, which means you have some unknown parameters in the PDE. So sometimes we want to estimate the distribution of the solution, right? So what we have, what we use the PDE for is to just use it to propagate. We learn a part of the some terms we have interest, like let's say the solution, the distribution of a solution, and we want to see the, let's say the boundaries, or something. I mean the violation conditions of that. Then we use the PDE, we propagate via the PDE equations, to get other terms. So it's still, you can think it's a transport of the probability mass. So after you define a map, so you can always transport the mass from from a probability space. So the equations can serve as kind of such a transport. So we just use that to get other terms. Yeah.
This is more suggestion, maybe it comes across as trivial. So when you were talking about uncertainty and ensembles, you talk about the initial conditions. Those are more ways in which you could create ensembles. And I wonder if it could help you train the model with different data subsets or other ways. So there are many ways of generating ensembles in this type of model.
Yes, yes. So yeah, I mentioned, so in the when we talk about uncertainty, there are, I mean, there are a lot of sources of uncertainty. Like, so the reason why I talk a lot about the initial conditions is just because it's widely used in the weather forecasting area. But you're right. So like in the hyperparameters of the PDE, it can also be random. So that is why they call it a random PDE. Anyway, so if the hyperparameters are random, that means when, yeah, let's say if the initial conditions are certain, we know it for certain. That means we have different transport. We have different map to others. But still, if we know, I mean, during the inference, if we know the parameters, yeah, there is no uncertainty. What we get is just a solution map for sure. But if sometimes we even do not know the hyperparameters. So let's say back to the weather prediction. Yeah, we know it's driven by a Navier-Stokes equation, but still there are some other terms, other unknown terms we don't know. So we cannot even have this kind of well-defined map to transport them. But if we just learn a map, you can think about it as, yeah, it's a simplified model. We just learn a map that can be equivalent of all the underlying maps. So using this map, we can get the transport of the mass. So somehow it's a simplifying. Yeah.
I think we'll call it there. I'd like to thank our speaker again.
Okay, thank you.